Hi, welcome to another quick video. I'm working on a right number function, so you can just come along and drop in any font. I've made it available for previous displays, including the ILI9341 recently. This display is a little unusual. Each byte written represents 2 pixels. Using Microelectronica's font creator, each byte represents 8 pixels. I have to look at each position within that string of bytes, look at the first 2 pixels, then assign them to a high nibble and a low nibble of a byte, then write the data to this screen, then look at the next 2 bits, assign each bits again to the high nibble and low nibble, and do that for the length of the font. I've made 2 important discoveries. Let me show you. So this is the font creator I'm talking about. Hopefully you will have seen it from my previous videos. Right, I've drawn a picture in Paint, otherwise you will never understand what I'm talking about. Using Microelectronica's font creator, you could see on that screen I'm drawing the number 0. And the first byte in that font array, OXC0. Windows calculator, go to programmer, hexadecimal, 0xC0, and there's the binary representation down here. So these binary digits represent the pixels on the screen. So if we have a look at this, well, we've got nothing, 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 nothing. So 1, 2, 3, 4, 5, 6 spaces before the first pixel. There's the array up here. Hopefully you can see my mouse moving. 0xC0. So 6 spaces. 1, 2 on the calculator. 2, 3, 4, 5, 6. So immediately you can see that byte comes to us back to front. There's 6 spaces, and there's the first 2 pixels there, there and there of the first byte. Then you get a second byte, then third byte, so on and so forth. That's the first problem. The bits or pixels are reversed, so you have to go through each byte and reverse them. But it doesn't matter whether you're going forward or backwards, you still have to go through the byte, so it makes no difference at all whether they're reversed or not. So that's character 0. I can get rid of this now. So this is the first byte of the font for number 0. That's the binary representation. So first byte, 8 pixels. So pixel there and a pixel there, represented by the 1s, and all the rest are empty, so no pixel of them showing down there. So the SSD 1327, which is that round screen you saw, in normal mode writes 1 byte per 2 pixels. That's confusing, isn't it? That's why I drew it out. I thought you'd never understand with me trying to explain. 1 byte for 2 pixels. Yet that byte represents 8 pixels. So I'll show you the code in a second, how I worked it out. So we start from the bottom end because the pixels are back to front. So bit 0, bit 1, remember you work backwards, 7, 6, 5, 4, 3, 2, 1, 0. Bit 0, bit 1. To confuse you further, the SSD 1327 has 4-bit color depth per pixel when in normal mode. I'm sure I've got a note there somewhere. So each pixel has 4 levels of intensity. So 1111, full intensity for a pixel, then 1110, slightly less, 1100, slightly less again, and it goes on and on. So 4-bit color depth per pixel. If you're not familiar with bytes and nibbles, have a look at my bytes and nibbles video I did the other week. So for 2 pixels at full intensity, we need the high nibble, 1111, and the low nibble, 1111. So the low nibble equals 15, high nibble equals 240. You should be with me so far. It's all there graphically, so you can't get it wrong. So I take this first nibble, follow the red arrow, multiply this first position by 240 to give me the high nibble. Now if there's a 1 there, it's going to multiply by 240 and give me 240, which will give me a high nibble, full intensity. If there's a nothing there, nothing multiplied by 240 is still nothing. So that will give me nothing, which means that pixel will not be on. Then take the second bit, So bit 1, multiply this by 15 to give me the low nibble. And again, if there's no pixel there, I'll have a nothing. If there is a pixel there, I'll have a 1, which multiplied by 15 gives me 15. So the data out to the screen, high nibble, ORed with the low nibble. Do that 4 times per byte and repeat for every byte in the font array stroke string. Simple. When I developed the number 0, the number 0, that's the character I started with, this is how I did it. So you've got a high nibble and a low nibble, and there's the local variables. You've got a J, which just runs through the font. So let's assume this is character 0. That'd be a 0 for J equals 0 up to the length of the array, and then J++. So that's what that for loop is doing. Then you can see here, high nibble equals number font, JJ, and 0x01, so that first bit. Then the low nibble is the same byte, but the second bit. The second bit would be a 2, but I want to know if it's just on or off, so 1 or 0. So I take the 2 and shift it 1, which is, as you've seen in my previous videos, shifting it 1 is the same as dividing it by 2. You could do that if the high nibble is greater than or equal to 1, but as we've all learnt, if there's a 1 there, it will return a 1, and this will be a 1. So you don't have to put if it's greater or equal to 1. So if you've got the high nibble equals F0, which is 240. Otherwise, it equals nothing. So that you don't have to do that, but it's prudent to do it. If it's not equal to 240, you want it equal to nothing. So if we've got a low nibble equals 15, otherwise it equals nothing. And that's how I went through it. So the data out, high nibble ORed with low nibble. Then I repeated it for the second 2 bits. So bit 4, shifted 2, will give me a 1 if there's a pixel. Then bit 3, shifted 3 places if there's a pixel. And I went through the whole code like that. But so if I build this, so this is the right number 1. This is how I developed it. Then I thought this is awfully long just for one. If I try and get it all in this screen, it's awfully long just for to write one character, i.e. the number 0. So from there, we've still got some running off the screen. I know I've got spaces in the middle, but so from there all the way down to there is just the character 1. So then this morning I was working through it and I came up with this solution. Get rid of all the ifs and everything and just sort of do some of the maths in the place where you write the data. So the high nibble is still at first position, low nibble still the second position, and then I just let high nibble. So write the data out, high nibble times high, and the high I've got as a constant 240, and then ORed with low nibble times low. So low nibble times low, low equals 15. So if we've got a 1, it's multiplied by 240 to give us a pixel. And if we've got a low nibble, it's multiplied by 15 to give us a pixel at full intensity. And then I'll look at the second and third, fourth and fifth, sixth and seventh. It's dividing that byte into 4 bits per pixel. You see there, 4 bits per pixel, 1 byte out, 2 pixels. And I was quite happy with that. But then I thought I'll mess about with the debug tool, see if I can get it to run through this code. So first of all, if you're not familiar with the debug tool, and it doesn't always work on all chips, so run start debugger. Right, so I've already run this today, so the stopwatch comes up, or the watch clock comes up, and this list thing, watch values here. But if you haven't got them, run up to Tools, View, Debug window, and you can look stopwatch, breakpoints, RAM window. if you haven't got them, so that's where you add them. So I've sussed out the easiest way to go through some of this, and I've deleted a load of code, so we've just got the basics. Hopefully you can see my mouse moving up the right here. So we want to, where it says lot tris A, that's where it started, so step over, and it gives you the time down here in the stopwatch window. Hopefully you can see my mouse moving, how long it takes. And I've checked it, this microcontroller is running at 8 megs, not the 64 which is capable of. It was only running a clock the other day. Setting tris A, so setting port A as outputs, took 0.50 microseconds. So back up here, where is it? Step over. Step over, step over, step over everything. Unless you want to know the time, but you can watch don't forget to watch the clock in the bottom window. So like this delay, for example, you can see it's a delay of 100 milliseconds. So hopefully you can see my mouse moving. When I step over it, we should have 100 milliseconds. A 100 millisecond delay should take 100 milliseconds to complete. So let's see, step over, there we are, 100 milliseconds. So step over, over, over. I want to get down to my while 1 has got draw 0 and draw 1. Right, here we are. We're down to the draw 0, so right number 0 is where I think I have optimized my function to write the character 0. And you saw number 1 was longer, had a lot more stuff in it. So let's see how long each bit takes. And you can see I've repeated it here on the screen. Hopefully you can see my mouse moving. So right number 0, so we're going to step over it. Now watch this clock down here. It's really important. Right 0, step over. 14.76 milliseconds. It is a large font. So that right 0 with my optimized function took 14.76 milliseconds. And you could say, oh, the function looks nice. Now watch when I step over this number 1. Up here, step over, hover over your buttons on your debug tool, and it'll highlight what they're going to do. So step over the number 1. Hello, 13.6 milliseconds down here. I don't know if my window will be flashing with me clicking this mouse down here. So number 1 took 13.6 milliseconds, and as I said the other day, all your code, nanoseconds add up to microseconds, and microseconds add up to milliseconds, so you've got to be careful with your code, especially when you want fast numbers. So that number 1 took 13.6 milliseconds. It took a shorter time than what I believed was my superior code, which wasn't the first code I developed. The first code I developed with all the simple ifs, anyone can understand, that's actually superior because it's faster. So, and again, so step over this number 0, 14.76 milliseconds. Step over the 1, 13.6. Step over the 0, 14.76. Step over the 1, 13.6. So there we have living proof. I think I can shut this debug window now. It doesn't always work, and it's really difficult to use if you don't use these step over functions. If you use a run to cursor, it takes forever. So right 0. So I don't want to bore you with all the code, but for those of you who are experienced, so I've still got the high nibble and low nibble, blah blah blah, checking the bits, and then I'm writing the data. So no ifs or elses. This took 14.76 milliseconds, and it's nice and compact and tidy, and This first code I developed yesterday or last night, near midnight actually I got it going, and once I got one character on the screen, by dropping in any font I like, I developed a 0, then for the 1 through to 9 I just copy and paste and adjust a couple of numbers here. It's really good. And now I can drop in, or you can drop in, any font you like for this type of screen. And that's what I've been doing on the previous screens, the ILI 9341. I've got the SSD 1963 coming up, probably in a day or so. So this longer routine, or which looks longer, is faster and superior. So that's one shocking point. Write number 0 is 618 bytes. So it's shorter than my write number 1. So that shorter function took longer to run. That was shocking. Here's something else that's even more shocking, which is the final shocking bit of my shocking video. Right, if I take these local variables, cut, paste, this is all live, right, paste them there. This is what I thought this morning. If I paste all those there, get rid of them from all the write 0, write 1, write 2 to 9, and then the space, it's bound to take up less room, isn't it? So I forget, before I build this, let me remind myself, because I'm talking, I always forget. So the write 0, which I'm on, 618 bytes. And I thought I'll just use all the functions, we'll just use these global variables. That's what you always do, isn't it? No, watch. I've forgotten already with my talking. 618, was it? 618 bytes. Now with these variables taken out of the function, they're now global, and my intention was to remove them from all the other functions. Build this. It's bound to be smaller, isn't it? Because it hasn't got these. I mean, that's a byte, that's a byte, that's a byte. Yeah, and there are 2 more bytes there. So I've saved 1, 2, 3, 4. I've saved 5 bytes from that function. Wait for it. So write 0 was 618. That one. Right, I looked earlier, looking for it down here. Couldn't find it. Write 0. Hello, it's jumped up. 690. By removing those variables and making them global, it's increased the function size by a massive amount. Considering I'm writing, 10 numbers, 0 to 9, plus a space, I was trying to save space. The write number in a colour display is just 1 for 1 pixels, and each write 0, write 1, write 2, etc. is only about 218 bytes long. But you can see for this display I've got to do a lot more work. But so it's jumped up from 618 to 690. And because I'm talking, I can't do the maths in my head. Standard. So 690, take 618, 72 bytes increase. And what I haven't tried yet, now they are not local, they're global variables. So build, so look, run, start debugger. Let's see how long it takes, see if it makes any difference to the length of time it takes to run. Right, step over. So my initialized display, which it's just about to step over, there is one point that switches on a power supply, and then I wait 300 milliseconds for it to stabilize. So this initialized display should take at least 300 milliseconds. So if I'm watching the clock down here, step over it, there we go, 400.25 milliseconds. So this debug tool is really great once you get the hang of it and if it's working. This is just a build, a normal build. I'm not running this from the chip. So step over, you can see how long each function or bit takes. Right, here we go. So 0, they're now global variables. And I haven't checked this. So and I forget how long it took. Was it 14.76 or something? Step over. That's a new number. I definitely do not recognise that. 17.55. I think it's taken longer. I'll tell you why. So 0 is still the same, 13.6. Step over 17.55 for that 0. Step over the 1, 13.6. And step over this last one, 13.6. So shut this window. Back up to my right 0. First of all, I was shocked that removing all this increased the size of this function. I'm not shocked that it's now taking longer because something in the IDE and compiler has to link all of this with this. So I'm not surprised at all it took longer. That's why I always said bit banging is actually really fast. No call functions, no nothing. It's all there in front of you. Anytime you have a call or a for loop or a while one, it all takes time, as I demonstrated in a video just the other week. So, proof that global variables cost more in time and a lot more in space. I was really shocked. Hopefully you've learned something. I certainly have by messing about with the debug tool today. I've also learned having a long-winded code isn't always a bad thing. This function for right number 1 is over 1 millisecond faster than this right number 0. And I'm shocked. I've learnt 2 important lessons today, and I hope you have too. Unless you already know, then if you already knew, leave a comment. But yes, I've learnt that having a long-winded looking code isn't always a bad thing. It can be superior and faster. And I've learnt taking variables from a local and making them global costs you space, a lot of space. If you like this video and found it helpful or informative, don't forget to click like. It does help me and help other people find this video. Thank you for watching.